All right, well this video is for the, let's see, I think it's the fourth handout on sequences. And I'm focusing on this because there are a lot of concepts that we can talk about that really kind of relate to a lot of the important ideas of calculus. So we were talking in one of the previous videos about limits, right? Kind of reviewing what we had talked about back in the fall. And if you remember, we had this definition, and I didn't make a big deal about it, but it is kind of a big deal in calculus, that says, this is the definition of a limit, that for all epsilon, there exists a delta such that x minus a less than delta means that f of x minus L is less than epsilon. And this is in saying that the limit as x approaches a of f of x is equal to L. So as these are closer, then these are closer as well. Okay? And the visual representation for this, right, was that we had an A here, and we had our L up here, right? And this is the L plus epsilon, L minus epsilon, and then down here around A, we've got A plus delta and A minus delta. Okay? And so what this definition is saying is that as you get closer and closer and closer into A, you should be getting closer and closer and closer into L. Okay? That there's no place where this is going to jump out of this little region that we've identified right here. Okay, so that's for the limit of a function. Now, for the limit of a sequence, it works a little bit differently. So what we're going to change here is we're going to change that f of x to a sub n. We're going to change the limit to as n goes to infinity, and then we're going to keep the L. Okay? And so we'll change this to a sub n. And then, let's see, up here what we're going to say is that there exists an n greater than some big N, such that, let's see here, what do we want to say? We want to say that, right, oh, there exists an n, so that for all little n's bigger than that one value, our limit will be very, very close to the value of the sequence. Okay, so now that we've got that set up, let's talk about it a little bit. How is this different? Well, what's different here is that the n is going out in this direction, right? And then what we're saying is that somewhere out here is this big capital N, and then here's our limit L, and we've still got L plus epsilon and L minus epsilon. Okay, and I'll use a different color here. Let's say we've got our terms here. There's A1, there's A2, A3, and let's say it's doing this. Okay, and then what we're saying is that at some point, there we go. This is going to kind of stay inside here. Okay, so that's what this statement is saying. All right, is that if we define this region around the limit, at some point out here we should find a point where all of the sequence terms fall within that region. Okay, and we'll have some sequence terms that are outside of that region, but we need to find this big N so that all of the sequence terms after that will fall within this region. Okay, so that's what we're going to do, and we're going to do this explicitly. We're going to find that number for some of these sequences. All right, so let's look at some of the problems on the handout number 4 here. All right, so problem 2. see. A sub n, this is our sequence, is 2 minus 1 over 10 to the n power. And the instructions say determine the limit L, so we want to know what's L. And then determine the values of n for which a sub n minus L is less than epsilon. And we've got these 4 different values of epsilon. In part A, we want epsilon to be 1/11. In part B, it's 1 over 150. In part C, 1 over 999. And in D, 1 over 1500. And that's just putting different widths on that region that I had drawn up here a few minutes ago, right? There's our L, this is L plus epsilon, and this is L minus epsilon. So these different values of epsilon make this region kind of thinner or fatter, okay? That's what we're looking at here. And correspondingly, the values of n that we're looking for will be bigger or smaller depending on how skinny or fat that region that we're interested in is. Okay, so first off, we want to know what's the limit. Well, as n goes to infinity, this part's going to go to 0, and so our limit's going to be 2. Okay, now, with this scenario right here, absolute value of a sub n minus L, that's the same, let me write this down. If you've never thought about this before, this is an important idea, right? Absolute value of 5 minus 3 is the same as the absolute value of 3 minus 5. They're both 2, right? This one is a positive 2 both inside and outside the absolute value, but this one is a positive 2 once it comes out of the absolute value anyway. So these are the same. So what I'm talking about here is that if the a sub n is bigger, we can just throw away the absolute values, okay? If the a sub n is smaller, I'm going to flip these around and then get rid of the absolute values because they're going to be the same thing in the end anyway, all right? So hopefully you'll see that as I'm going through these problems, because if we're subtracting away from 2, we're coming up to 2 from underneath it. So let's draw a little picture here. Here's our L at 2, right? And let's say these are our L plus epsilon and L minus epsilon, and we're coming up from below that, right? We're going to start, a sub 1 is going to be 1.9. I'll just write these down. A sub 1 is 1.9. A sub 2 is 1.99, and so on, okay? And so we're going to start, let's say this is 1.9 right here, so we're going to start here, and this, like that. Okay, and so that's just sort of a rough sketch for what we're working with here. All right, now let's do some algebra. So a sub n is 2 minus 1 over 10 to the nth power minus L is equal to 2, and we want that to be less than epsilon. In this case, 1 over 11. Now, the 2 and the minus 2 cancel each other out. This is negative 1 over 10 to the n power. If we take the absolute value, that'll just be positive 1 over 10 to the n power. Okay? I could have switched those and written this like 2 minus 1 over 10 to the n. This is what I was doing earlier when I was saying that a sub n, if you're working with absolute value, a sub n minus L and L minus a sub n are the same thing. And so here, the 2's will cancel out just like they did before, and we end up with the same thing. 1 over 10 to the nth power less than 1 over 11. Okay, now here's a neat trick. I don't know if you ever thought about this before, but if you've got 1 over A greater than 1 over B, that means that A is less than B, and vice versa. Okay? When you take a reciprocal, it flips this around, in the same way that multiplying or dividing by a negative does, and for a similar reason, right? Because we could cross multiply here, and it would change sides. I don't know how interested you all are about that, but I find it pretty cool. All right, so I'm going to take reciprocals on both sides, and we'll get 10 to the n should be greater than 11, and that means that n needs to be greater than 1, right? Because 10 to the first power is 10, any other power is going to be bigger than 11. All right, so that's part A, n just needs to be greater than 1. Now let's go to part B. The only thing that's going to change is the value of epsilon. Now for part B, 1 over 150. And the way to solve this numerically is to take a log base 10 on both sides, right? If you do log of 150, you'll get the answer. And I'll do that in 1 minute here. Just by looking at this, you can see n needs to be bigger than 2, right? Because 10 squared is 100. Any other power of 10 will be more than 150. Now, we'll run into some that are not as easy as this. And like I said, to solve this numerically, what you would do here is take log base 10 on both sides. The n comes down in front. And in this case, log 10 is 1, and so we just need to calculate log of 150. And so this says n greater than 2.176. We're only dealing with whole numbers for these sequences. N can only take on whole number values, 1, 2, 3, 4, and so on. So saying that n is greater than 2.176 is the same as saying that n is greater than 2, right? Because the next whole number is 3 in either case. All right, let's see here. So that was part B. Let's do part C. 1 over 999. Oh, this is where we took the reciprocal. And this is the same thing, n greater than 2. Okay? If you take the log of 999, it's going to be 2 point something. 2.999. So 3 would be within this distance of the limit. So that's also n greater than 2. And then part D, 1 over 1500. 1500. Here, n greater than 3, right? Because 10 to the third power would be 1,000. So the next whole number, 10 to the fourth power, would be 10,000. And then all the rest of them would be bigger than that. And so again, this is n bigger than 3. And you can solve this numerically by taking the log of 1500, which is about 3.176, right? So again, n greater than 3 would give us that value. Okay, so that's problem 2. Let's look at a few more of these. All right, what's next here? Problem 4. We've got a sub n, 1 over the square root of n plus 1. Right? As n goes to infinity, that denominator will become infinitely large, which means that the fraction itself should go to 0. All right, what do we have here for epsilons? 1/5, 1/10, 1 over 100, and 1 over 1,000. Okay. So in this one, with the limit being 0, we set this up 1 over square root n plus 1 minus 0, less than, we'll take the first epsilon there, 1/5. Okay, so this is, we don't have to mess around with anything in here. This is just absolute value, 1 over square root n plus 1. This is positive, right? N is always a positive number. N starts at 1 and counts up. Right, from there. So we don't have to worry about this being negative. We can take off the absolute values. And there we go. Now, take the reciprocals, flip the greater than or less than sign. And now we want to solve for n, right? Square both sides, subtract 1, and there we go. n greater than 24 will make this within 1/5 of our limit, which is 0, n greater than 24. So, and we can test this out, right? Let's take the first term where n is greater than 24. 1 over square root 25 plus 1. So 1 over the square root of 26. .196 approximately. See how it's less than 0.2? That's 1/5, right? And then all of the other terms will also be less than 0.2. So that's what this is doing for us. And this is one of the fundamental ideas of limits, is this idea of how close exactly do you need to be to this limit. Just tell me, and I'll make sure that you can get closer. I'll pick this out to make sure that you're as close as you need to be. All right, so let's put in the other epsilons here. 1/10. So that'll be 1/10. Take the reciprocal. Now this is 100, and then that'll be n greater than 99. Okay, now let's make this 100, 100, 100. This will be 100 squared, which is 10,000, and then that'll be 9,999. And now let's see, let's make this 1,000, 1,000, 1,000, and then when we square it, let's see, we need 1,000 squared, which is 1,000,000, and then this will be 999,999. Okay, so that's problem 4. Let's see what else we've got here. Problem 6. Let's see here. All right. Problem 6 is 128 over 2n. 2 to the n. There we go. Okay, so again, the limit here as n goes to infinity, this denominator is going to become infinitely large, the numerator is going to stay where it is, and that's going to send this limit to 0. All right, what are the epsilons we're interested in? This is 1/10. 100th. You can use the decimals if you want to. It doesn't make any difference. But since I'm going to take reciprocals, I'm going to stick with the fractions. All right. So let's see here. So let's take this. Whoa. A sub n is 128 over 2 to the n power minus L is 0. And our first epsilon is 1/10. All right. So again, with this 0 here, this is a positive value. We don't really need to worry about these absolute values here. And there we go. All right, now let's take reciprocals. 2 to the n power over 128 has got to be greater than 10. That means 2 to the n has to be greater than 1,280. So now this is where that numerical solving that I was talking about comes in handy. Okay, so we can take a logarithm on both sides. I'll use log base 10 in this situation. Log of 2 to the n, log of 1280, and log 2 greater than log 1280. So n needs to be greater than the log of 1280 divided by the log of 2. So let's see what we get here. So this is you might need to review your properties of logarithms a little bit in solving logarithmic equations to make better sense of that. But that's how you bring a variable down out of the exponent. Okay, so this log of 1280, and if you're typing this into your calculator, don't forget to close that parenthesis, okay? Okay, so this is approximately 10.322, so we can just say n greater than 10, right? The next one's going to be 11, and that'll do it for us. So n greater than 10. Okay, let's see what else we've got here. So now we want to change this to 100. That'll be 100, that'll be 100. That'll have an extra 0, 12,800. And now we need the log of 12,800. So n greater than log of 12,800 divided by log of 2. So let's see what that is. About 13.644. So we can just say n greater than 13. Okay. All right, now we want this to be 1,000. Put another 0 on there. 128,000. And now let's make that calculation. Uh, 16.966. So we can just say n greater than 16. Okay, last one. Make this 10,000. Put an extra 0 on there. Now this is 1,280,000. There we go. And now we need to calculate the value of log 1,280,000 divided by log 2. And there it is, 20.288. And so down here we can just say n greater than 20. Okay, so that's problem 6. Like I said, this one's a little bit tricky because of this solving for n process right here. Okay. But, like I said, you can review the process for properties of logarithms and how to get that variable down out of the exponent. And if you have any questions, just please let me know. You can also talk to Kelly. You know, she's got that remote math lab set up. All right, so let's look at problem 8. Let's see what we've got here. All right, problem 8. Let's see, I've got a bunch of this whiteboard chemical dust here. There we go. Okay, problem 8, 5 plus n over n plus 1. Okay, so remember what happens to a fraction like this as n goes to infinity, right? The difference between n and n plus 1 becomes almost indistinguishable. So this thing is approaching 1, right? This is the ratio of the coefficients because those powers are the same. So this is going to end up being 5 plus 1. Now this is another case where the limit is actually bigger than the sequence terms. It's coming up from below the limit. And so I'm going to kind of, well, I mean, we can look at it both ways. I did this, I think it was problem 2 that was like this as well. But let's go ahead and set this up. So we're going to have 5 plus n over n plus 1 minus 6. Let's see here. Less than epsilon. Well, let's see. So this would be n over n plus 1 minus 1. Now this is negative. This is a negative value right here. N over n plus 1 is less than 1, right? If n is 9, this is 9/10. It's less than 1. So when we subtract this, our answer is going to be less than 1. So what can we do about this? Well, my answer to this is to just flip these around. 1 minus n over n plus 1. That's what I was saying at the beginning about the, absolute value of 5 minus 3 is equal to the absolute value of 3 minus 5. So that's what I've just done here, is to flip those around and make this positive. Let's see. What are our epsilons in problem 8? Okay, so these are just 1/10, 1/100th, 1,000th, and 1/10,000th again. All right. So let's start with a 10th. All right. What are we going to do here? We've got some choices. One thing we can do is we can move this to one side. We can put this over to the other side. We can also make a common denominator here, right? This will be n plus 1 over n plus 1. I think that's how I'm going to approach this. So now we'll have a common denominator of n plus 1. This will be n plus 1 minus n on top, right? Those n's cancel each other out, and we're just left 1 over n plus 1 less than 1/10. That means we want n plus 1 greater than 10 and n greater than 9. Okay. Let's put that down. And now all the rest of these are going to work in a very similar fashion. Just like you saw me just adding zeros in that last problem. There we go. N greater than 99. And then for this to be 1,000. 999. And this one is going to be 9,999. Okay, so that's the first set of problems on this handout. Now let's look at these last 4 problems, 9, 10, 11, and 12. I'll do 10 and 12 and leave 9 and 11 for you all to work on. All right, so problem 10. This one's a little bit tricky because of that fraction. And 12 is a little bit tricky as well, but let's talk about number 10. So this one, so our a sub n is 2 to the n minus 11 over 4n minus 7, and we're saying that the limit here is 1/2. Okay? The way the problem is set up, it just has the absolute value, 2n minus 11 over 4n minus 7 minus 1/2, and our epsilon here is 100. Okay. So, what are we going to do? What are we going to do inside the absolute value here? Well, one thing I would do is I would find out which one of these is bigger. Is this coming up from underneath? Is it coming down from above? Because that's going to tell us whether this thing inside here is positive or negative. So let's just make n equal to 10, and then we'll calculate what this is going to be. So if n equals 10, then this will be 20 minus 11 on top, 40 minus 7 on the bottom, and this is going to be 9 over 33. Considerably less than 1/2. Let's see. What if n is 1,000? Then this will be 2,000 minus 11 over 4,000 minus 7. You can see this is much closer to 1/2. What is this? 1,989, and this one's going to be 3,993. And I suspect that that's also less than a half, but let's see what we get here. 1989, 3993, yeah, 0.498. So this thing is always going to be smaller than a half, so we've got some choices to make. I'm going to choose to swap these around to make this positive, okay? So then we'll have 1/2 minus 2n minus 11 over 4n minus 7, and we want that to be less than 1/100th. Okay. So again, I'm going to make a common denominator here. All right. Let's see here. Over here, we'll need to multiply by 2 over 2. Over here, we multiply by 4n minus 7 over 4n minus 7. Now, like I said, there are other ways to go about doing this. You can get the half and the 100th together. You can move this to another side. Maybe I'll go through this solution first, and then I'll come back and I'll do it the other way. Okay? All right. So let's finish this up, and then I'll come back and solve this the other way for people who don't like common denominators. All right. So this one's going to be 4n minus 7 times 1 minus 2 times 2n minus 11, right? Here's the 2, there's the minus. And our denominator is going to be 2 times 4n minus 7. And then this is still 1/100th over here. So what do we get here? 4n minus 7 minus 4n plus 22 on top. 8n minus 14 on the bottom. Okay, so those 4n's cancel each other out. 22 minus 7 is 15. And now we can take reciprocals. 8n minus 14 over 15 greater than 100. Multiply on both sides by 15. 8n minus 14 greater than 1500. And then we want to divide this by 8. So that's going to be what? 189. And then, what's the left over there? Going to be 0.25. Let's see. 1514 divided by 8. Yeah, 189.25. And so we can just say n greater than 189. Did we answer the question? Find the smallest value of n that does satisfy the given inequality. 190. Okay. All right, because that's the first one after 189. So let's see, let's make this n equals 190. All right. And in this case, we just had a single value for epsilon, that 100th there. All right, now let's go back and solve this the other way, okay? So let's get this. So what can we do here? Well, let's see here. It doesn't matter how we approach this. Let's say I like to move this over to this side so I don't have to worry about that negative sign, 2n minus 11 over 4n minus 7. And that means we need over here to do 1/2 minus 100th, and we haven't done anything that would flip that around. This is going to be 50 over 100, so that'll be 49 over 100 on this side. And then let's see, let's cross multiply. Multiply here by 4n minus 7, 4n minus 7, and then also multiply by 100. So those cancel, and we get 49 times 4n minus 7 less than 100 times 2n minus 11. Now, if you're doing this, you always have to be careful about, are you multiplying by something that is negative, right? This is positive, though. Let's see here. As long as n is bigger than 2, this will be positive. And our n's that we're interested in are going to be bigger than 2, right? So that's not going to flip this around. But you do have to worry about that sometimes. All right. So now, let's see here. 49 times 4 is going to be, what, 196n. And then, let's see, 49 times 7 should be 343. Yeah, 343. This will be 200n minus 1100. So let's move everything over here. There's 4n, and then add the 1100 over here, and that'll be 757 divided by 4, n greater than 189.25, just like we got before, 190. So there's a different way to do the same thing. If you don't like making common denominators, then you can do it this way, and this works just as well. Okay, that's problem 10. Now let's take a look at problem 12. All right, so in problem 12, now this is not part of the problem, but we can pick out this information from what is in the problem. And our limit here is 1/5. All right, and let's see, what's our epsilon? Well, let me write that down. So now what we're working with here, 5 to the n plus 2, 5 to the n plus 1 plus 5, minus 1/5, and we want that to be less than, what is that? That's a 10,000. Okay, so let's see here. Is this positive or negative inside here? Well, let's do this with just n equal to 1. Okay, if n equals 1, this will be 7 on top, 30 on the bottom, so this that should be bigger than 1/5, right? 7 divided by 30 is 0.23 repeating. That's bigger than 0.2. So this one's bigger. So this thing is positive to begin with, and so we don't need to worry about the absolute values. So let's just take them off. All right. Okay, so first off, let's see here. Let's make a common denominator again, and then I'll go back and I'll solve it the other way too. All right, so here, to make a common denominator, we've got some choices here. I'm just going to multiply by 5 over 5 here, and then by the other denominator, 5 to the n plus 1 plus 5 over 5 to the n plus 1 plus 5 over here. So this then, let's see, so our new denominator is 5 times 5 to the n plus 1 plus 5. Up here we get 5 times 5 to the n plus 2 minus parentheses 5 to the n plus 1 plus 5. Because that negative is going to get distributed inside there. Okay, now what? Well, let's see. We need to do some combining of like terms. Now, it's important to remember this. When you do 5 times 5 to the n, that's going to give you 5 to the n plus 1, right? When you multiply two things with the same base, you add their exponents. And then we'll get plus 10 minus 5 to the n plus 1 minus 5. And then we've got our 10,000th for epsilon over here. Now, the reason why that's so important to know what you get when you multiply 5 times 5 to the n is because now these cancel each other out. And we're just left with a 5 on the top, 5 times 5 to the n plus 1 plus 5 on the bottom. Those cancel. And here it is. This is where it gets a little bit easier. Okay, take the reciprocals, 5 to the n plus 1 plus 5 greater than 10,000. So 5 to the n plus 1 greater than 9,995. And now we need logarithms again. Okay, so take a log on both sides. So n plus 1 log 5, log 9,995. Let's see here. So, n plus 1 needs to be bigger than the log of 9,995 divided by log 5. So let's just get a numerical value for that. So, log 9,995 divided by log 5, 5.722. So n needs to be greater than 4.722. So that means the smallest value of n that would work, n equals 5, right? That's the first whole number after 4.722. Okay, now let's go back and see what would happen if we did this without making those common denominators. I'm not sure how this is going to work because I haven't done it myself yet, but we'll take a look at it. All right, so what are we going to do here? We're going to add 1/5 to both sides. Less than 1 over 10,000 plus 1 over 5. I'll just use the calculator. I like common denominators. I'm happy to make this into a fraction so that we take the reciprocal later. Plus, well, this is going to be 0.2001, right? Because this is 0.2 and this is 0.0001. So there it is. All right, so now we multiply on both sides by 5 to the n plus 1 plus 5, so those cancel. So this is 5 to the n plus 2, less than, let's see here, 0.2001 times 5 to the n plus 1 plus, what is that going to be? 1.005, right? Let's see here, 0005. Yeah. Okay. All right. Let's see here. Now what? See, now I'm kind of stuck here. Let's get the 5s on the same side. So I'm going to subtract 5 to the n on both sides and subtract 1.0005 on both sides. So that'll cancel, and let's see what we come out with here. So that's going to be, what is that? Right, 0.9995. Well, that's good because we've seen that number before. This is going to be 0.2001 times 5 to the n plus 1 minus 5 to the n. All right, well, so this is where it gets a little bit tricky. So if you were hoping to do this to avoid the trickiness of making a common denominator, now you've got a factor of 5 to the n out of this whole mess. That'll leave you with a 5 here and a 1 there. Right? Because when you multiply this back through, there's the extra 1, 5 to the n plus 1, and when you multiply this over here, there's your 5 to the n. So, let's go ahead and calculate this. Right, this is going to be 5 times 0.2001. I think we just did that. That is, yeah, 1.0005 minus, well, I'll write it down. 0.005 minus 1, so that's 0.0005. So, divide on both sides by that, 0.005. And that's 1999. And now we need logarithms again. Log 5 to the n, 19 log of 1999. So n needs to be bigger than the log of 1999. divided by the log of 5. So let's see what we got. Log 1999 divided by log 5. So this is n greater than 4.7, or n equals 5. Well, again, some problems, there's just no easy way to do it. Okay? So there's some interesting things in this problem. As always, if you have any questions, if you run into some problems in doing these, please let me know. I'll do a follow-up video for the last handout on sequences, and then we'll get started on talking about series, finite and infinite series.